All right, we should be live for World Quant office hours. Okay, so let's go ahead and get started. We spent yesterday working through T2 of the mini project of the ML mini project, the Go Data course, and apparently my pod has shut down, so I'm going to go ahead and launch that up once again. Let's see who is with us so far for office hour. I see Raydot. Welcome, Raydot. I see Wally. Hello, Wally. Abu Bakr. Hello again. Reman. Hello, Reman. Starting a little late today because I had something else in there, so apologies for that. We'll, of course, end 15 minutes later, so we'll have an hour. Balak Emmanuel here, Mickey Rat. All right, welcome everyone. And let's continue our march through the ML mini project. Any questions about Q2? I did recall that I was running something and it was not going to run anytime soon. It actually finished shortly after office hours, and we had a model that didn't do any better. Did not do any better. Oh well, that's how we perform these experiments, to see what is going on. In fact, I didn't clear out my output. And just to show you, there it is. Same score we got last time, 156. So here, as we probably have anticipated, the imputer strategy mean was the best, but it probably doesn't have much of an effect, frankly speaking, on the end result. So once again, one of the things you want to keep in mind is you can look at all the options you have available to you, all the experimental options you have, and you're going to really have to narrow that down, right? We could really spend a lot of time and effort picking out the best imputer strategy. But if we just know from our experience and we can rationalize that median is probably the best and frankly mean probably don't get much different results, then why waste time tuning the strategy? We can just stick to median and focus on more important things. One of the things we'll make sure we do is let's focus on the more important things that will have a drastic effect on our model's performance. So that just comes from experience, just come from doing these things as we go through these mini projects. All right, I see Fatima is here. I see Esau. I see Mickey saying, Don, would you talk about what is multilinear regression model stacking ensemble techniques? Seemingly train a data set using separate model pipelines and then merge the results together. Exactly. All right, I can I can talk about that. In fact, we could maybe try to do something like that in this question here. All right, looks like Wally's a fan. Great to hear. I see Ogun Toki and Joakim. Okay, so Mickey is bringing up an interesting question. Is what if we have several models? In fact, we kind of built two models. We kind of built the KNN model and we built the logistic regression model. We built two models. And so let me just draw a picture as we have, right, I'll call it predictor 1, predictor 2. Maybe a logical name for that. Predictor 1 and predictor 2. Here comes the data, and we get out results. So at the moment, run it, get out two results, and we're just choosing the best model. But maybe there's a way where I can combine two models to come up with a better outcome, a better result. Maybe there's a better way I can combine these two models to get a better result. And what we want to do essentially is we want to stack these two models. So what I'm going to do here is I'm going to say the following. I'm going to figure out how to blend these two models together. It's kind of like when so let's say whiskey. Whiskeys are made, or certain scotches are made from a blend of other scotches. And the question is, well, what is the best proportion, right? Same thing happening here. How do we best blend these two outputs? So for example, we want to come up with an overall better prediction. I'll call this Y double hat, just out of lack of characters. Well, that's a little awkward. Let me just come up with a better, I'll call this YP, Y-pred. And I want to come up with a better prediction that's going to combine or blend these two models. Instead of just choosing one or the other, why don't we just use both of them and blend them together? And for my very first approach, I will blend them as just 1/2 of one and 1/2 of the other. That is my initial strategy here. Initial strategy. Blend one and one together. 1/2 of one, 1/2 of the other. Sorry, 1/2 of one, 1/2 of the other. What are your concerns about this simple approach? What are your concerns? What do you worry about this simple approach? Of course, the fact I'm saying it's simple suggests maybe there's a better way. But can we critique this way to blend our two models? Well, I guess my criticism, or one of the things I would want to know, is why 50-50? If we say 50-50, we are saying that both models are, we should equally weight both models. Right, that's sort of what we're saying here. We should equally weight for these two models. Yeah, well, exactly. Why not different proportions for both models, right? Why not maybe come up with a better weighting scheme than 50-50? Right? Maybe a better weighting scheme is kind of the following. Maybe a better weighting scheme is something like y of p and maybe 0.75 plus maybe 0.25 for the second one. Why don't you use a different proportion? So I see a comment here. Wouldn't that bring about inconsistent results? What do you mean by, can you elaborate what you mean by inconsistent results? What do you mean by inconsistent results? So maybe this is a better way to blend y1 and y2. So really, we have another question, is how do we best blend the two models? How do we best blend our two models? Well, in some sense, we can just generalize this. We can generalize it by saying the following. We can say, well, we have a YP, our overall model, is a blend of some fraction of our Y1 model plus the blend of our second model, Y2. We were generalizing what we had before. First, we said 50-50. Then we said, well, why not use different proportions, or why not enable using different proportions, because 50-50 may not be the best bet. Now we sort of think it's 75-25 is just an example of a different blend. And now we can generalize it by saying there's a weight in front of Y1 and a weight in front of Y2. The weight in front of model 1 and weight in front of model 2. What does this resemble? What does this look like? What does this look like here? This has a resemblance to something we've seen before. This is only for numerical predictions. What if that's why it's regression? We could have done something slightly different and done it for a classification, it would have been which model gets the most votes. Which is a little weird since you have two models. You'd have three models instead, and say which one got the most votes. So you can adapt it for classification. You can adapt it for classification. But here, strictly speaking, Mickey, as you pointed out, is just for regression. Our Y's, our labels, our numerical results. Good point. What does this resemble, this that I've written out? Doesn't this resemble linear regression? Right? Isn't linear regression we have y, and we have maybe beta naught x of 1 plus beta 1 x of 2 plus beta 1. Probably should erase that. Plus beta naught. A weighted average we can kind of view as sort of linear regression. So this resembles linear regression, right? It resembles linear regression in which that alpha 1 is, this should have been, I haven't flipped around. I don't know why I did that. Flipped around there. Make the correction. There you go. Alpha 1 is beta 1. And y1 is x1, and so forth. Right here, we don't have an intercept. We could, right? We could have generalized this. We could have said, you know what? Let's add an intercept term. We could have done that. A constant term. So notice that the fact that it resembles linear regression, well, and then our model's predictions, our separate model predictions, are sort of like features. Right? Those are features. Those resemble features. So it looks like our model's predictions resemble features, and the proportion we blend them are model parameters. So what if we do something where we basically we take our two models and we come up with a feature matrix. And we are learning, and we learn how to best blend those two predictions to come up with an overall prediction. Right? This is called stacking or blending. Because you're stacking two models to get a better model. You are blending the results of two models to get an overall better prediction, or in the hopes of getting an overall better prediction. This is here, when you use more than one model to come up with the result, it's called an ensemble model. And there are various ways you can achieve an ensemble model. This is one such way, blending or stacking. Questions about this approach or this idea? Okay. So in fact, there's a way to do in scikit-learn easily these days. Scikit-learn stacking. There's stacking classifier and there should be stacking regressor. So stack estimators with a final regressor. So there we go. This is a built-in way to do it in scikit-learn. So here we're blending ridge CV and linear SVR. And we're using a random forest to best blend them. So maybe at the end of this mini project, maybe we can come back to that. Maybe we can go back and see if we can blend several models together. We'll put a pin on that, but it's a good topic to discuss. All right. Let's move on. We'll consider using blending later on in our journey. But now let's go ahead and move on. Okay, so let's look at the question 3. The ownership and the certification columns contain categorical data. We will have to encode the categorical data into numerical features before we pass them to an estimator. Construct one or more pipelines for this purpose. Transformers such as label encoder and one-hot encoder may be useful here, but you may also want to define your own transformer. Okay, and then combine them with the feature union. Okay, so we have it set up here. And as always, I'm kind of skeptical about the code we have. I'm always skeptical about the template code we have. So I'm just going to kind of ignore that. And let's see where that takes us. Okay, so we have ownership. Let's look at data. Let's do kernel and restart and clear output. Let me go and run the cells I need. Cell, run all above. And let's just be judicious about what I need. I need the 2 data frame. I probably need the column selector. Let's not worry about pipeline at the moment. All right. So say data. Let's look at ownership. Okay, they appear to be texts. Let me look at unique. Okay, those are the unique values. I can know how many there are. 13. 13 categories for ownership. And three unique values for certification. We have 3 there. Okay. So I want to encode this categorical data. Remember how my machine learning predictor, it wants numbers. It wants tabular data as numbers. So if I have categorical data, nominal data, I need to encode it. And one such scheme is our one-hot encoder. So let's go ahead and get that done. So what we'll go ahead and do here is I can say, construct my workflow. What I want my workflow to do is I want to, here comes the data. I want to convert it into a data frame. I want to then give it to my column selector. And I want to feed that into my one-hot encoder. So my data frame, my column transformer, followed by the one-hot encoder. And of course, a final predictor here. That's sort of the workflow I want to set up. So let's go ahead and get that settled. So I can say from sklearn, import pipeline. What should we call this model? A model. How about this? How about categorical features? What I will have here is two data frame. My selector, so my column transformer, I'm going to give it ownership, followed by certification. And then I will give it my encoder and my one hot encoder. So I've got to make sure I import that. So there's my pipeline. Let's try that out. Categorical features, fit in transform on data. Okay, that seems to have worked out. I have 16 columns. Makes sense because one hot encoding will create one feature for every unique value in my category. All right, that's cool. And let me go ahead and create my model. So I basically wrap these three pieces in a pipeline, and then I will wrap this in a pipeline. Categorical features model, pipeline. And what I'll have is I'll have my, I guess I'll call it features, categorical features. And since I'm doing regression, sorry, classification, let me just stick to logistic regression. What is it? Greater than 0? Yeah. Find counts. Okay, that seems to have run. Okay, we can always look at stuff like the score, right? Categorical features model, score. Okay, about a 70% accuracy. Okay, well, we'll keep that in mind. This here is probably code that meant to confuse us and trip us up. I'm feeling arrogant about not having to pass the assert methods. Just comment out everything. Let's submit that to the grader. Got a name error because I don't have that positive probability function defined. So I would define it there. So I run that there. We got a score of 0.937, so not too bad, right? Not too bad for a simple linear model. Questions we will have before we try to improve on this, before we try to improve what we got. All right, question for you is, what can I do to improve the model? And since I find this code here distracting, and I'll just erase it. What are things I can do to improve my score? This is our benchmark, our very first benchmark model. It's not our final model. Maybe so. Maybe we can't do any better. That's perfectly fine. What can we do to improve, or what are attempts we can do to try to improve our model? Whether it does so or not, that's a different story, right? We carry out these experiments. What can we do? I'll jot several things we can do. The very first thing we do is tune our model, right? Tune our model's hyperparameters. Right? Before we even think about trying a different model, well, let's just tune these models' hyperparameters. We haven't even done that. Maybe feature engineering generation, especially since we have a linear model. And maybe the last resort is try an entirely different model. I set these in a hierarchy here. They have a hierarchy because the first one's the easiest thing we can do. The easiest thing we can do. The second thing involves, well, creating, polynomial features perhaps or something like that. And really the last one's entirely in a different model is repeating once again. Okay, I see Ash here is, hey there, Don. I am from August 2020 cohort. I hope you are doing great. Is there any way that I can join for Unit 2? Because unfortunately I couldn't continue till Unit 2 the last time. So Ash, you're the more welcome to join office hours. If you want to formally take the course, I got some potentially good news for you. I've heard that the applications for Unit 2 for January might reopen soon. So I suggest you look at the you look at the WorldQuant Apply website, the application website, because I believe that Unit 2 applications will open up soon. Of course, when they do open up soon, you have to sign in the same way that you applied so that we recognize your account and be able to offer you the application for Unit 2. So 2 things. You're more than welcome to stick around for office hours, or you can try tomorrow. I don't have a definite date when it will reopen, so you might want to try every day for several days. But I believe the Unit 2 applications will open up soon. And thus, if you are a Unit 1 alum, Ash, are you a Unit 1 alum? So I want to make sure of that. Well, if you are a Unit 1 alum, make sure you sign in with the same account you used to have Unit 1. So we recognize you that you are an alum. And then we can give you a application for Unit 2. So try out tomorrow. Yeah, you are. Good to hear. So and then you can join us for the January session. You can come back to us and you can join us for the January session, which will start up in the middle of January. I think January 17th is sort of the just Unit 1. Okay, perfect. Because all you got to be is a Unit 1 alum. So if you know the application website, the WQU Apply, now I see. So today's your lucky day because I believe the applications will open up tomorrow. Or at the very least, they're going to open up within a week's time. So check tomorrow, apply. Make sure you sign in with the same account you used for Unit 1 so we recognize that you're an alum. It's very crucial. Because if not, there's no way we're going to know that you're an alum and then no way to offer you an application. All right, so I think today's your lucky day, Ash. Thank you for reaching out. So now that you're aware of that. So hope to see you in January then. All right, so go ahead and pivot back here. So I put these in a hierarchy because, well, the first one's the easiest thing to do. Right, so before we even do something radical like try an entirely different model, which has its own set of problems, own set of hyperparameters we have to tune, let's just focus on tuning our model's hyperparameters. And since we're using a very simple model, logistic regression, it only has one key hyperparameter, C. So let's see how we can best tune that. In fact, there is a nice logistic regression CV that's got the cross-validation already built in. And we'll give it an alphas range. I think it's C's. And we'll give it a log space. Typically, you want to give a log space for these regularization parameters. And let's see what happens. Okay, that ran. Let's see what our training score is. All right, Peter. Nice to meet you again. And our score isn't not that much different, it looks like. Well, let's see what happens when we submit to the grader. And not that much different. So it looks like, you know, we probably get the most of our model. Take the last step. Let's see what, I want to figure out what the best parameter was. I don't know on top of my head. C underscore is probably what to store under. So it looks like that was the best C value. Probably could have looked at the documentation. Let's see. Attributes. The array of C that maps the best score across every class. So that's what it figured out. So C underscore was the best C that we found. All right, office hours timing. Office hours are, I forget. Monday, Wednesday, they are my time at noon, which is 16 UTC. Tuesday, Thursday, they are at 20 UTC. Tomorrow, next week, I'm out for 2 days, so it's going to be a different time. But those are primarily the times we've been doing. Okay, so that was okay. So we can probably try a different model, right? A more powerful model. Let's try that out. Let's try a more powerful model. So from sklearn, let's try our decision tree. Import decision tree classifier. That, of course, has its own set of hyperparameters. So we'll, from sklearn, model selection, import grid search CV. So grid search CV, decision tree classifier, param grid. Let's try 2 to 20. 5 folds, verbose equals 1. Let's try that out. Let's go ahead and replace this. And let's see if we can do a better job with grid search. I mean, with max depth. I mean, not max depth, decision tree. Let's see. We tried that out. And it looks like the same score, right? Not too much different. I can say best params, max depth of 7, and let's submit it to the grader, and oh, looks like I have a score that does slightly better than the reference solution. Okay. I see a question here. Peter saying, is TDI offering fellowship program for students outside of the U.S.? I think it's very difficult to get a fellowship spot if you're coming from outside the U.S. for the TDI fellowship program, for the free program. It's very difficult if you're coming from outside to the U.S. because you can imagine the way we want people that can be easy to place. So can't say any guarantees, can't say one way or the other. I would say it's very difficult to get the free slot if you're coming from outside the U.S. Okay, so questions about what I did. Okay, do let me know. But I think we've got enough. We got it. We beat the reference solution. We can kind of move on. Notice our approach, right? Our approach was let's get something that works. May not work the best. Get something that works, and then let's go ahead and improve on it. So we try to improve on it by tuning that hyperparameter of C of our logistic regressor. Okay, then we said, hey, let's try a different model, and we did, and we got success in terms of a better model. So this iterative process here, right? Let's not just jump to the fancier models. Let's stick to something simpler, get that to work, because we sort of built the upstream piece, and then we improve. I'm requesting for some light on the one-hot encoder. Go for it, Esau. Go and let your question be known. Let's go ahead and clarify that and fix that up. What's your question? Okay, let me know if there's something particular about the one-hot encoder that's you're not understanding. Do me let know if there's a specific question about the one-hot encoder so I can kind of start from explaining. Considering working with many different types of estimators and not only R squared as a score, we should always look at comparative scores, right? Considering working with many different types of estimators and not only R squared as a score, should we always look at a comparative? We should always look at the cross-validation score is what we really should be looking at to be strict. In fact, I probably shouldn't be using the grader to infer what is the best model because I'm potentially overfitting with respect to the grader. So I really should have taken my my grid search object and said -1 and looked at best score, because this here is the best cross-validation score. And now notice that I'm doing this a classifier. So classifiers, R squared is for regressors. So here I'm using accuracy as my metric because I have a classifier. So you use whatever metric makes sense given the type of problem you have, regression or classification. All right, so Esau, yes. So let's explain a little bit what's going on with one-hot encoder. So what's going on with our one-hot encoder? Question about will there be deep learning after this? No, there is no. Deep learning is not part of the core curriculum. Deep learning is not part of the core curriculum. I think deep learning gets too much emphasis because I think a lot of our problems can be solved without going to deep learning. Whether we get to talk about office hours, that's a different story. But officially, no. All right. Okay, one-hot encoding. Let's say we have a column of categorical data. Let's say, for example, we have red red, green, blue, and green. Red, red, green, blue, green. What is -1 in the model? So this here, this categorical features model is a pipeline. It's a pipeline object. Right? If I say type categorical feature model, it's a pipeline. Since pipelines are a sequence of steps, then it makes sense how that one would be able to index into the model, index into the pipeline. So if I want the first step 0, I say index 0. 1, right? There's only 2. There's only 2 steps. And since my predictor is my last step, -1 as the last step. So that's what that represents here. I can index a pipeline object just like one would with a list. And since my predictor is the last step, I can use a -1 index. Remember how I can use negative indices to count from the back? Exactly what I did here. So let's say I have red, red, green, blue, and green. My predictor needs numerical data. That's one of the things that we're learning, we're going to get more comfortable with understanding, is that our predictor needs numerical data. We give it text data, it would spit it out, so to speak. Of course, that doesn't mean that we can never work with text data. It just means we have to encode it. We have to process it and work with it. That's why we have all these transformers. So we have to do all this pre-processing to get our data into the right format for our picky eater. So what if my first attempt to encode this data is to say that red will be mapped to 0, green will get mapped to 1, and blue gets mapped to 2. So in other words, what if I apply this encoding scheme? So if I look at it, follow the rules, red to 0, green to 1, blue to 2, that means I have 0, 0, 1, 2, 1. Okay. Now, this solves the problem of my model needing numerical data. But what do you think is wrong with this type of encoding scheme? I can train my model now, but what will be a problem? What do you think is a concern here? See, Yusuf is here. Hello, Yusuf. What is the concern? Let's start with the zeros, right? The zeros is okay, but maybe something what my model might learn, it inadvertently, is that there's a hierarchy. My model might learn that, well, that red is less than green and less than blue. Our model might learn inadvertently this hierarchy. It might learn that blue is equal to twice as much as green. And this is a problem. My model might just be fixated on this. So notice how I've imposed a hierarchy here. I've said that green is bigger than red and blue is bigger than green. I've solved the issue of encoding the data so that our model can use it, but it's going to misuse it. And that's not necessarily any good here. It doesn't make sense why blue is greater than green and greater than red. We could have chosen a different mapping. It's arbitrary. These fields you just can't compare. You can't do comparisons with them. So we got to be a little careful about how we go about encoding this data. So let's try a different way to encode the data. Let us create 3 columns. Since we have 3 different categories for that column. So we're going to create 3 new columns. Those columns are is red, is green, and is blue. Let's extend this here. So, and then what we do is, since this one is red, well, that means it has a value of 1 for that column, but since it's not green or blue, it would be 0 for everything else. Red again, 1, 0, 0. Green, 0, 1, because it's green, and 0. Blue, well, that means 0, 0, and 1, and green would be 0, 1, and 0. So notice a different way to encode it. I take a column and I create k number of new columns, where k is the number of unique categories in that column. And those columns are is red, is green, is blue, is category 1, is category 2, is category 3, is category k. And notice there is only one true value, only one value in the array. It's a little weird the way it's phrased. Every row of those 3 new columns, there's only one non-zero value. How about that? Only one non-zero value. I circled them here. Now they look like zeros. Hence the name one-hot encoding. Hot to be turned on. Only one of those new columns is turned on, is hot. Questions about one-hot encoding? Okay. All right. Cool. Got that resolved. Okay. Other questions about Q3 people have? Okay, let's move on to Q4. Finally, we'll combine simple features and categorical features in a feature union, followed by an estimator and a pipeline, or more precisely, a predictor. You may want to optimize the hyperparameters of your estimators using cross-validation and try engineering new ones. When you've assembled your trained model, pass the predict proba method to the grader. Okay. Well, actually, we don't pass the predict proba method. We just rely on this function to do it for us. Oh well. And once again, I find this template code distracting and probably not to lead us to a good solution, so I will comment it out. And so what we want to do is we have two pipelines that we've created. We have simple features. Oh, so we have categorical features. So I can sketch out my diagram. I call it my categorical part, my cat pipeline, and I have, what else? My simple features. My simple. And I want to combine these two steps in parallel. I want to wrap them together. I can wrap these together using feature union. So that the next step is maybe a predictor, for example. Grid search explain, please. Yeah, so what about grid search you need explaining? Just so I can make sure I know where to start from. So what about grid search is confusing that you need some sort of insight on, just so I know a good place to start in my discussion? All right, so I'll try my best to start from scratch there. All right, so we want to determine what is the best hyperparameter value. So for example, we've been playing around with logistic regression, and we were playing around with a value called C. And there are various values of C we can try out. So in fact, if I go over here, max depth, for example. Max depth of 2 to 20. So we're saying here, this dictionary represents the values, represent what values to try out for a given hyperparameter. So here we're saying specifically here, try out 2 from 19 for max depth. So we give the model we want to tune, there it is, decision classifier. We give it the param grid so it can then construct a grid of all the candidates to try out, which is just max depth from 2 to 19. It's going to apply k-fold cross-validation. In other words, it's going to run 5 experiments to determine which is the best hyperparameter. We set verbose equal to 1 so it can print out what it's doing. If we don't set verbose equal to 1, we see an asterisk and we just kind of hope that it's actually doing something. So So by saying verbose equals 1, we're going to see a printout of, a little update of what's going on. So when we call fit on our model, when it fits the grid search, it starts tuning the model. It starts figuring out, was 2 the best hyperparameter for max step? Was it 3? Was it 4? Was it 5? Was it 6? Was it 7? All the way to 19. It will run its k-folds experiment to determine what was the best one, and then it will retrain the model with that best hyperparameter, that best configuration. You can think of hyperparameters are configurations of our model, things we set before fitting. They're going to guide and ultimately dictate the model parameters. So we're trying to find out what's the best configuration for our model to do, and Grid Search CV allows us to do that. Yeah, why do we use it? We use it to figure out what is the best configuration of our model, the best hyperparameters. And the reason we do it is because choosing the best hyperparameters will give us the best model for predictions. It will give us a model, hopefully, that doesn't underfit and a model that doesn't overfit. Because when we set the configurations of our model, we want to make sure our model doesn't make sure we want the model that learns enough from the data, but doesn't start to memorize it. So grid search is used to figure out what is the best configuration of our model so we can have the best generalized predictions as possible. That's the purpose of grid search. It's a tool to easily do this for us. Okay. Follow-ups? Anything else? We got 2 minutes, so I'll just kind of sit here and take a couple quick questions. All right, I see a question here. Suleiman, is it right to say that one hot encoder is good or no variable while label encoder is for nominal variables? Label encoder should only be really used for your labels, your labels Y. One hot encoding is preferred when you have nominal data because it doesn't impose a hierarchy. Or no encoder. So we have one hot encoder. One hot. Probably should call that one hot. Too many O's. One hot is for nominal data. Basically, data you can't say is this one's greater than that one. There's no hierarchy. Nominal data, no hierarchy. No ranking, if I can use that simpler term. So countries, right? You can't really impose a hierarchy on countries. Ordinal encoding, which is what I drew before, ordinal encoding. The label encoder in scikit-learn is mostly used for labels. Ordinal encoding is for ordinal data. Data where there's an order to them. So maybe we had categorical data that is bad, okay, good, and great. There's a hierarchy in those labels. There's a hierarchy in those categories. So we use a ordinal encoder instead. So one hot encoder, nominal data that has no hierarchy, that you can't compare one to the other. If we can compare those categories to one to the other, we use ordinal encoder instead. So we impose a hierarchy that makes sense for that data. So basically the question is, does it make sense to impose a hierarchy to say one is bigger than the other? If no, one hot encoder. If yes, ordinal encoding. All right, time is up. I have to head out. Everyone take care. Have a good rest of your day, Friday. And I'm going to be out for 2 days next week. I'm going to be out Monday, Wednesday. So Russ, the other instructor, will fill in for me at a different time. At a different time, I'll make that announcement on the board, and it's also in the email. So it's a different time. It's a different time next week for just Monday, Wednesday. It'll be 12:30 UTC Monday, Wednesday. So Monday, Wednesday of next week, 12:30 UTC. Of course, consult Jupiter Hub. As always. CV is the number of folds. How many experiments we run, basically. Param grid is a dictionary that maps what hyperparameter and what values to try out. And verbose is going to print results out to the screen so we know what's going on. All right,